Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Chapter 17, putting those discriminant analysis methods to use for the purpose of classification. So the goal with discriminant analysis from last chapter might be used to classify individuals of unknown origin into one of several known groups. So how should this be done? Recall that our example from last time, we had two subspecies of an insect, and they were compared on two external features, which we called feature 1 and feature 2. And the discriminant analysis gave one discriminant function, can1, so canonical direction 1, which gave us the best ability to distinguish the subspecies. And so it makes sense that we can use canonical direction 1 to classify insects because that's the best linear combination of the features that distinguishes those species. So if we look at this example here, this is pretty much what we had last time. We had feature 1 on the horizontal and feature 2 on the vertical axes. We had two populations, subspecies 1 and subspecies 2, and we found that the direction in this downward sloping direction was canonical direction 1, the direction that best discriminates these two subspecies. So the previous paragraph, so given a score of can1 on each insect to be classified, we want to assign insects to the subspecies that they most resemble. And similarity can be measured as the distance on canonical direction 1 to the average canonical scores for the two subspecies, which I've identified with X's. So on this conical direction 1, this downward sloping line, if you observed a new observation, say where my crosshair is in the upper left-hand corner, that observation we can project down onto this axis, the canonical 1 axis, and then we can ask, is this crosshair, the new observation, closer to this X, which is the center for group 1, or is it closer to the X for group 2? And whichever one it's closer to, that's the group to which we'll classify this new observation. Which means that once we design a classification rule, we'll use that rule to correctly, we hope, identify with high probability new observations that we encounter in nature. Right. So here's an example using the Fisher's iris data. We have canonical direction 1 along the horizontal axis. That's the one that gives about 99% discrimination. And then canonical direction 2 only gives about a little bit less than 1%. And the question is, say we observed this new observation here, observation 1. To which species are we most likely to classify this? Well, we would look at the distances from the new observation to the means for the three different populations. It seems pretty far from Setosa, and it's closer to versicolor, the green one, than virginica, the blue. So we're likely to classify this as versicolor. Observation 2, very clearly, we would classify as Setosa. And all this brings up the concept of distance and what type of distance we mean when we're looking at the distance from observation 1 to the means. The standard Euclidean distance is one strategy, but there are better strategies than that. In particular, the Mahalanobis distance, which I will continue to say Mahalanobis distance because it's so fun to say, is a way of defining distance not only by the Euclidean distance, but also based on the shape of the distributions. So there's covariance, say like in the blue group, or maybe the red group is even better. Look at the distance or the shape of the red group. There's negative correlation here, and
it's much longer from the top left to the bottom right than it is across the other direction. So when you say what is a point that's far from this distribution, you have to consider the shape of the distribution. For example, observation 2 is fairly far from the distribution. There's lots of blank space before there's any observations in the Setosa group. But this distance is not very long. In fact, if this observation 2 was rotated over here, it would be well within the distribution of the data. But when it's rotated to the left, so it's down to the bottom left, it's actually pretty far from the distribution. So Euclidean distance itself is not enough of a description for distance when we're talking about distributions of data that have covariance between, in this case, the canonical directions. So the Mahalanobis distance, I'm so good at pronouncing this word, and I've messed it up twice now. The use of the Mahalanobis distance is a way to correct for the covariance between the features. So suppose we've got p features, so we've got an x matrix, x vector that has p features in it. So in the iris data, that was the petal length and width and the sepal length and width. That was 4 dimensions. And we had 3 groups, k equaled 3 groups. And for each of those groups, we can calculate the mean over the 4 or the p features. And we can also calculate the covariance matrix, which is 4 by 4 in the Fisher's iris data, of the covariances between the 4 features. And from that, finally, we can calculate the pooled variance covariance matrix, which is simply a weighted average of the variance for group 1, the variance of group 2, and up to the covariance of group 3, or however many groups you have. And it's weighted by the sample size in each group and divided by the total sample size minus the number of groups. That gives us, if in fact the covariance matrices are equal, this gives us the best estimate of the shared covariance that all groups have. So the Mahalanobis distance is defined, so classification rules can be defined in terms of either the Mahalanobis distance or in terms of a probability model. We'll in fact actually be sort of mixing these together in a moment. So that Mahalanobis distance is, so we'll call it d squared. So this is actually the squared distance. I mean, you guys know how to do Euclidean distance, right? I just want to bring up the equation very quickly for Euclidean distance. So if you have 2 points P and Q over n different dimensions, you take the difference between between those two measurements for any dimension and square it. Take the distance between the points for the next dimension, square it, and so on. Add all those up and then take the square root. If you think of just doing the first 2, that's basically what you get when you're doing the Pythagorean theorem. A squared plus b squared equals c squared, but then when you find the distance c, you take the square root of the a squared plus b squared. And a is the distance in one dimension, and b is the distance on the other orthogonal dimension. And so that's what's happening here. This distance, the observation minus the mean for sample I. So in our case, for the Fisher's iris data, we've got Setosa is say the first group. So that's when I equals 1. So this is the distance between the observation and the mean. And so is this over here, x minus x bar. And these are both vectors, so we have a whole bunch of distances. And if we ignore the s in the middle for a moment, when you multiply this vector transpose
times this vector, that's like taking the square of each difference and then adding them up. So that is exactly taking the square of each one and adding them up. It's what's underneath the square root or radical symbol. Now what the S does, or S inverse, is it weighs this square distance by the covariance that exists between features. And that will shape the distance such that this observation 2 that's only, let's say that this was 1 inch away, even though inches don't make any sense on these axes, but on the screen, say that was 1 inch away, that is actually very far when you're in this direction, whereas if observation 2 was rotated around to be in the thick of this data, this 1 inch is not very far. And so that S inverse matrix is going to convert our distances by the shape of the data. Let's take a look at an example. So these ellipses give equal distance from the center point for this distribution, so that when you go out 5 standard deviations along the long direction, you get miles away from the center, whereas if you go the other way, 1, 2, 3, 4, 5, it doesn't seem that far, but in terms of the Mahalanobis distance, those represent the same distance from the data. So let's take a look at an example where we've got 3 groups. We have features x1 and x2 on the axes. Group 1 is black, group 2 is red, and group 3 is green. And we have 3 observations. Here's observation 1, right in the thick of group 3, so that's very obvious. It's closer to the center of group 3 than it is to the centers of group 2 or group 1. Here's observation 2, sort of on the fringe of group 1. In fact, you can see 1, 2, 3, 4, 5 bars. If you went out one more bar, it would probably be there in ellipse 6. Whereas in terms of the distance from group 2, 1, 2, 3, 4, 5, 6, 7, 8, maybe 10 standard deviations away or so. So this would clearly be put into group 1. Group 3 is the interesting one here. In terms of Euclidean distance, it's actually closer to group 2, this straight line distance with a ruler, than it is to group 1. However, because of the elliptical nature of these distances, this observation 3 is right on the fringe of being 5 units away for group 1, but you might need, so this is 5, 6, 7, it's sort of somewhere between 7 and 8 perhaps units from group 2. So this point, even though the Euclidean distance is closer to group 2, its Mahalanobis distance is closer to group 1. Therefore, it will be classified with group 1. Group 3 never had a chance. All right, so that's what all that says. All right, so the Mahalanobis distance from the ith group to the jth group, basically that's saying how far are the pairs of groups from each other. You can calculate the same way. I'm just putting in the ith group and the jth group. For example, we can think of in the example above, maybe we want to compute the distance from group 1 to group 2. So these two plus signs, how far are those the centers for those two groups? So we can just simply plug in I and j, and the order doesn't matter. The distance from I to j is the same as from j to I, and we would just plug everything in the same way. And we can ask, basically, how well are we likely to discriminate between pairs of groups? When groups are more similar to each other, they're going to be harder to distinguish. So in the plot above, groups 1 and 2 are closer to each other than group 3 is to either of them. And group 3 seems to be slightly further from group 1 than from group 2. So we're likely to classify very well observations from group 3, but groups 1 and 2 we might have a little bit of confusion there.
And by confusion, I mean misclassification. All right. So the Mahalanobis distance classification is equivalent to classification based on a probability model that assumes the samples are independently selected from multivariate normal populations with identical covariance matrices. So this assumption of equal covariance matrices we will relax by the end of the chapter. But let's start with this assumption in place. This assumption is consistent with the plot above, where these elliptical clouds are identical for all three groups. All right. Suppose you can assume a priori, so that's before you've seen the data, that a randomly selected individual from the combined population, meaning imagine you're a fisher and you're out looking at irises and you see a new iris and you're just assigning it as you know it's an iris, but you don't know what the subspecies is. So that new observation is equally likely to be from any group. So one way of specifying that is our prior probability of that observation being from group J. So that's the notation I'm using here. In long notation, I'm saying the probability that the observation is from group J is 1 over K, K being the number of groups. So in the Fisher iris data, we had 3 groups, the Setosa, versicolor, and virginica flowers. So this is just saying the probability that it belongs to Setosa is 1/3, probability it's virginica 1/3. So given the observed features X, so you take that new iris and you measure the petal length and width, the sepal length and width, and that's our X vector for that flower, then what's the probability of belonging to group J, so group 1 would be Setosa, 2 is virginica, and so on, given the measurements we took on that iris? So that's what this says in long format. What's the probability that the observation is in group J given the features of that flower? And now we have this expression. And this looks complicated, but it is not that complicated. So the numerator, so we're asking, let's fix J to be 1. So let's imagine Setosa is group 1 for the Fisher iris data, and we've observed this new flower. And we want to know what's the probability that this observation is from group 1, meaning it's Setosa. So the way we would do this is we would calculate the Mahalanobis distance, the d squared, to the mean for, sorry, I'm getting all involved in my clicking. There we go. That d squared term, given these values from, so the distance from the observation to the mean of that group. So just as an example, imagine you saw observation 1 down here, and we're going to measure the distance from this X from observation 1 to the mean of group 3, and we're going to use the Mahalanobis distance. So in terms of Mahalanobis distance, this is maybe 1, 2, maybe 3 3/4 units from our observation to the mean, something like that. I'm counting the rings to get 2 3/4. And that is the d squared x part of that. Then we are going to divide by 2, take the negative, and then exponentiate or have that be to the power of the base of the natural logarithm, so e to that power. And that is going to be the numerator for this probability. Now, for the probability, we need to also see how far that observation is to the other groups. So in this denominator, we're going to add up, I'm having a bad time highlighting, we're going to add up the distances to group 1, group 2, and group 3, and the ratio of the distance to group 1 divided by the distance to all of them
is going to give us the probability of belonging in each individual group. And so we started off with a prior probability that the flower is equally likely to be from any group, and then conditional on the data that we observed for that flower, we now have a posterior probability of belonging in each individual group. And so we'll have three probabilities. What's the probability you were from Setosa, group 1, Virginica, group 2, or versicolor, group 3? And those three probabilities will add up to 1, and the group that has the largest posterior probability will classify that flower into that group. Okay, so we'll see some examples of this shortly. To evaluate the accuracy of a classification rule, there's different strategies you can go about. So the misclassification rate is often the thing that we care about, is a good yardstick to gauge a classification rule. Better rules will have smaller misclassification rates, and there's really no universal cutoff for what is considered a good classification for a given problem. There's certainly really messy data where you might be lucky to get a 20% misclassification rate, and then there's other sort of physics-based or engineering-based examples where a misclassification rate of 0.001% would still be pretty high. So what's considered good depends on the context of the problem. We've got basically two general strategies for determining the misclassification rate, and the resubstitution strategy is not that good, but you need to know about it, and we're going to focus the rest of this chapter on cross-validation. So in resubstitution, this evaluates the misclassification rate using the data from which the classification rule was constructed, meaning that we used all of the data to generate the classification rule, and then using the rules that were constructed with all of the data, then we ask of all those observations, based on the rule, would I have made the correct decision or not? And the problem this resubstitution strategy is a bad idea is because it's going to be optimistic. You've used the data to generate the rule that you then evaluate the rule with. And so you've effectively used the data twice. In fact, the observation you want to try to classify has already been used to generate the rule to classify it. So that's the problem. A fairer and better way to estimate the misclassification rate is using cross-validation. The basic idea here is that you use some of the data as a training or calibration set. Most folks say training sets. So you'll train the classifier with some portion of the data, and then with the rest of the data, you will test the classification. And that allows an external and independent set of data to be used to assess how well the rules you generated are for classifying. So there's the standard strategies for this are, let's see if I'm trying to find the words in the paragraph to point to. All right, so let's say a tenfold cross-validation. In tenfold cross-validation or k-fold cross-validation, you just pick some multiple. You'll divide the data set into 10 random partitions. And so those are, and in each 10%, you'll treat 90% of the data. I'm doing such a bad job of this. You'll use 90% of the data to train the classifier, and then you'll use the 10% that you didn't use as the test set and ask, in that 10%, how well did I classify? I actually know the true labels of the data set, and the classifier assigned labels, so I just match the truth with the classification. And then you're going to do that 10 times. So you've divided the data set into 10 parts. The first time, say you hold the first 10% out and you train with the second 90% and you perform cross-validation. Then using the same split, you take the second 10% of the data, use that as the test set, and use the rest as the training set. And then you do it the same thing with the third 10% and so on until you've done it with every 10% of the data. Ultimately, every observation gets to be used in the training set 9 times and as a test case 1 time. Other ways of splitting it would be a twofold, where you take the data 50-50. I think this is a sort of a poor strategy because you don't use very much data to train your classifier. What I really like, especially if you've got the computational power to do it, is the jackknife, which is an n-fold cross-validation. Effectively, you hold out an individual case as the test set, and then you use the n-1 observations as the training set. You develop the model, and then you ask of that single observation whether you would classify correct or not. And you do that for every observation. For some classifiers, this can be really computationally intensive, because if you have a large data set of like 1,000 or 2,000 observations, that's 2,000 times that you're running the same, you're fitting the same classifier. And if fitting classifier is computationally expensive, that can be sort of painful. All right, so LDA, it gives us the linear discriminant analysis. It's the Fisher's linear discriminant function, and it allows for jackknife cross-validation, which we'll see in a moment, and also allows us to use the predict function to do k-fold cross-validation, or to manually split the data and do training and testing. All right, let's look at the turtle shell example. So the carapace was the turtle shells. We have got males and females. And just as a reminder, this is the data from the previous chapter. And in terms of length, width, and height, the blues are males, the reds are females. Females tend to be larger than males. And in any one of these features, you tend to see a distinction between females and males. We're going to find a single direction that will do even better. And I want to show you some functions that help with classification. So we have a new function called partition matrix, which is a matrix plot that shows pairwise how well you can do for classification. So in the package KLAR, we've got the partition matrix function. Sex is our response variable, the categories we're classifying into, and we have 3 variables we're using as features. And I'm asking to plot the matrix of pairs of points. So I'm going to zoom in on this plot a little bit. In the top center, we have how well we classify if we are only to use length and width as classifiers. It shows here that we've got about an 18% error rate, which is pretty high, perhaps. And we have got a magenta and a cyan partition of the plane, with the decision rule being that boundary between the 2 colors. We have M's, which are males, and F's, which are females, and anything that's black are points that are correctly classified. It's the red ones that are misclassified. So any M's that are in the cyan side of the plot are misclassified. So we have this 1 M, and then looks like 1 M on the boundary. And then females in the magenta side are misclassified. So there's maybe 4 or 5 or 6 females over here. So that, if in total, if you look at how many errors you made divided by the total number of observations, that gives about an 18% error rate. If you look at length and height, that's this plot in the top right, we can, one more feature here is that there's 2 solid points, which are the means for each of the 2 groups. All right. In the top right, we have length versus height, and we see only maybe 2 or 3 females that are on the male side, and no males on the female side. So we have a lower error rate there of about 8%. And then if we look at width versus height, here we have some females that are misclassified, giving about a 15% misclassification rate. Our goal, of course, is to use all 3, but this gives you a sense of how well you can do pairwise and what those rules would be. All right. I want to show you the analysis and how it's visualized to generate a sense of using the linear discriminant analysis. So length versus height. Let me scroll up back to that plot for a moment. Length versus height. So that's this top plot. We're going to look at how this top plot comes to be numerically. Let's fit a linear discriminant analysis for sex versus length and height. And here the prior probabilities of belonging in male and female was 1/2. Those are taken empirically based on the relative frequencies of males and females in the sample. There were, I believe there were 24 shells in each group, and so that's coming from there. We have the group means. Those were the solid points that were plotted. And then the coefficients of linear discriminants. This basically defines the direction for classification. So we have a slightly positive length and a negative height that's 3 times that. So we want to identify that direction in the plot above. So a slightly positive length, a more strongly negative height. If I scroll up, so all right. I don't have the, well, I haven't figured out the ability to draw on here, but let's see. So length is on the vertical axis and height is on the horizontal axis. And what that said is that as you increase length, so as you go up in length, we're going to, let's start over here. As you go up in length a little bit, we're going to go to the left in height about 3 times as much. So if I go up 1 unit, so if I start in this bottom right hand corner, if I go up 1 unit, say in length, and then roughly 3 units in height, it's that direction that's the discriminant direction. And if I continue my mouse over that line, that direction, basically sort of left and right across that line, is the direction that the linear discriminant direction is in. And so that's exactly the direction that helps us best classify males and females. So this line that separates the cyan from the magenta colors is perpendicular to the linear discriminant direction. Okay, yeah, so slightly up with length, 3 times as much for height, but in the negative direction. And we call that LD1. Another way of looking at the output, if we look at it just in terms of, so the LDA.sh object. Let me scroll up for a moment. That's this one. That's this last one we did with length and height. LDA.sh. So the linear discriminant analysis for the shell data set. If I look at only one dimension of the data rather than showing the bivariate plot and ask about how well we classify into group female and to group male, the black bars here are females that are correctly classified, and we have 1 misclassification over here. So basically the rule here is if this axis, the linear discriminant axis, is roughly about 3/4, that's roughly the decision rule for being a female on the left and a male on the right. Down here on the male plot, the reds are the males that are correctly classified as males,
and the blacks were classified as females. And so here we've got 1, 2, 3, 4, 5, 6 misclassifications of males based on this plot. All right. This is a set of lines of code that we're going to use several times in this chapter. This creates a table that gives jackknife-based classification and posterior probabilities. So these classification error rates based on the jackknife is the n-fold cross-validation. And we're going to ask about whether it was classified as being male or female, whether that was correct. So we're going to start off with doing the linear discriminant classification using only length and height, just for demonstration. We'd probably ideally want to use all three variables here. Then I'm going to create a data frame, a table to hold our results. So we're going to put the true sex into a column labeled sex. We're going to take the classification from the LDA and put that into a column called class. So if sex and class, the classification, match, then there was no error. And if they differ, then there was a misclassification in one direction or the other. So I'm going to start with a column for error, and I'm going to have it start off with all blanks. So I'll just start by assuming that all the classification was correct, and then I'm going to fill in the errors that were made. And finally, I'm going to include the posterior probabilities for group what are the words? For group membership from the LDA. So for example, an observation might be 70% male, 30% female in terms of the posterior probability. And I'm going to then name these columns sex, class, and error. And then these two posterior probability columns are going to be post, and then I'm going to add the label from the posterior. So it's going to be post F for female and post M for male. Finally, I need to calculate what my errors are. So this is for the error column. I'm going to start by taking that error column and making it a character vector. Then I'm going to ask whether there's agreement between the sex, the true sex, and the classified sex. So right here what I'm doing is I'm taking the sex, which is a factor variable. So if it's a female, it's a 1. If it's a male, it's a 2. And I'm going to convert that to a numeric value. So it's either 1 or 2. And then this is the same thing but for the classification. So we've got the numeric sex, we have the numeric classification. If this was female, as the true one, it would be equal to 1, minus classified as a female would be equal to 1, and this difference would be 0. And those zeros would be put into this agree. Now, misclassification are ones that aren't 0. So if we had a female true sex, which was a 1, minus a male classification, that's a 2. So we have 1 minus 2 is a negative 1. So females who are classified as males are a minus 1. And vice versa. Males classified as females are a positive 1. And this last line basically updates the error column for those that did not agree based on whether agreement was different from 0. So if we look at the summary table here, classify.sh, we've got their true sex F, we have their classified sex, and whether there was an error or not, and we have their posterior probabilities. So these first two were actually classification errors. There were true females classified as males, that's why there's an error of -1, and the posterior probability for being males was relatively high, about 0.8 or 0.9 for each of these, and that's why they were classified as males. And what the error column allows you to do is very quickly scan down and see where there were errors. So it looks like there were 4 females classified as males, and all the males were correctly classified. Let me scroll up for one moment. Okay, those paragraphs above just describe what I'm going to say right here. So if I create a table using the sex and the classification columns in the table above and ask for the frequencies, you can see that of the 24 females, 20 were classified correctly as females and 4 were misclassified as males. And of the 24 males, they were all correctly classified as males. If you calculate the proportion by row, so prop table with the second argument of 1 means that we're going to look row-wise at the proportions. So 16% of the females were misclassified as males, and 100% of males were correctly classified as males. This diagonal of this table, of the prop table with 1, that's the row-wise proportions, are these two numbers. So that quickly gives you the correct proportion of classified observations for each group. If you take the sum, and so notice this prop table doesn't have an additional number. So imagine taking this prop table and dividing everything by 2. This diagonal is how many are correctly classified over all the observations, and the off diagonals are misclassified. So 91% of the observations were correctly classified, which gives an error rate of about 8%. All right, let's look at, you know what, I feel like that was a long video. Let me stop here. We'll come back to Fisher's iris data as an example, and then also talk about stepwise classification strategies.